State that gravitation provides the centripetal force for circular orbital motion. Now we know that planets go around the Sun in orbits. We also know that the velocity must be changing. How do we know that the velocity changes? Because velocity is a vector. Vector has direction. If the direction is changing, then the velocity is changing. A change of velocity means acceleration. Now, if there's an acceleration, there's an unbalanced force making something accelerate. And in this case, it's going to be a centripetal force, which is an unbalanced force towards the center of the orbit. It's always acting perpendicular to the path of the planet or the object in the orbit. This centripetal force is caused by gravity, the force of gravity, and here we have it. According to Newton, the force of gravity, gmm over r squared, will provide an unbalanced force, which is the centripetal force, which is m times by a, where a is v squared over r, the centripetal acceleration. So we have these equations, these terms are equal. So we can simplify them, and we end up for the orbital velocity. The orbital velocity is equal to the root of gm over r. You need to be able to derive this. It's easily done by equating the force of gravity with the centripetal force and solving for v. Now, we've seen an equation a little bit like this before. This is not to be confused with this. V is equal to root of 2gm over r. Where does that come from? This comes from the escape speed, or the escape velocity. Notice that the escape velocity has to be greater than the orbital velocity. An object which is in a stable orbit will not accelerate from the effect of gravity of the planet or the Sun. It has to be going faster by a factor of root 2. So don't confuse 2gm over r with gm over r. The root 2gm over r is equal to the escape speed, or escape velocity. This is equal to the orbital velocity. We have to be able to derive Kepler's third law, and it's basically the relationship between the orbital period and the orbital speed. Now, to sum up, what we need to do is to find out what the speed is, the orbital speed, in terms of the time period, the velocity and the radius. Find the orbital speed in terms of its velocity and radius and combine them and then cancel v. We want to get rid of v. So we'll start with this. The circumference divided by the time is the distance divided by time. This is going to give the average speed during the orbit. We know that the circumference is equal to 2 pi r. So v is equal to 2 pi r over t. On the other hand, remember that the force, the unbalanced force, is equal to the gravitational force is equal to mv squared over r, which is the centripetal force. This gives a value for v, as you know, of gm over r, the square root of all that. Now we can equate this velocity, which is the orbital velocity, which is the distance travelled divided by time, with the orbital velocity here derived from the centripetal force. Now, this way, if we equate these, we cancel v. So we squared everything. 2 pi r over t all squared is equal to v, which is gm over v squared, which is equal to gm over r. And we basically simply rearrange this to get it in terms of t and r. So we end up with, if we square this side, square everything here, we end up with t squared is equal to 4 pi squared over gm times by r cubed. So we basically can say that the t squared, the time period squared, is proportional to the radius of the orbit cubed. And this is Kepler's third law, and it's derived directly from Newton's law of gravitation. Derive expressions for the kinetic energy, the potential energy, and the total energy of an orbiting satellite in terms of r. Now we know a satellite has kinetic energy, which is half mv squared. We know that the orbital velocity is v, which as you know is root gm over r. So half mv squared gives us the kinetic energy is gmm over 2r, because we know this is v, which is squared multiplied by half m. This is the kinetic energy of an object in an orbit. Now we also know that the gravitational potential energy is equal to minus gmm over r. So we have the kinetic energy, we have the potential energy. The total energy is going to be the sum of the kinetic energy and the potential energy. We add them together and see if you can do this, and you should find out that the total energy is minus gmm over 2r. We need to be able to represent this graphically with the kinetic energy, the potential energy, and the total energy. This is the kinetic energy. It's a positive value, which is gmm over 2r. The gravitational potential energy is minus gmm over r, so it's always a negative value. So the sum of these two values will always give this value, which is the sum of the kinetic energy and the potential energy, which will be minus gmm over 2r. Notice that the total energy is always negative. It's always less than 0. If it were greater than 0, then the planet or the object will have escaped from the orbit. It would have left the orbit of the planet or the sun. So planets have a total energy which is less than 0. Discuss the concept of weightlessness in orbital motion in free space and in deep space. Now here we have these pictures of these oranges. They appear to be weightless. How do we measure weight? Well, we know weight by using a balance or a top pan balance or a Newton meter or something. So this appears to be weightless. Now it does not necessarily have to be weightless. What could be happening? This man could be in a ship which is in free fall, and it's not weightless. It's accelerating down. It could be accelerating down at the acceleration due to gravity, or it could be an orbit, because in an orbit which is traveling around the Earth is also in free fall. There's only one force acting on it, and that's the centripetal force or the gravitational force, which is going towards the Earth. So this could also be an object in free fall, which is in an orbit. It could also be out in deep space. If we were out in deep space, then that would truly be weightless. The first case is if he's in an orbit or he's in free fall, is not weightless. He is accelerating, but we're not able to see these observations. So the force measured is 0. We can still have a weight, but we have an apparent weightlessness. This appears to be weightless. Only when we're in deep space and we do not feel the effect of gravity, so we are truly weightless. So weightlessness is only for deep space. It might appear to be weightless if we're in orbit or we're in free fall, which are the same thing. And it's difficult to distinguish those two. And I will look at free fall and orbit in the next slide. If an object is in an orbit which is so fast that it accelerates towards the Earth and falls toward the Earth at the same rate at which the Earth curves away, then we basically have an orbit. But the object is still in free fall. It's still falling towards the Earth. But this centripetal acceleration, the centripetal force, is going to be the same as the acceleration due to the free fall. And so this gravity provides the centripetal force, which is going to be gmm over r squared. Okay, free fall. The person in the lift reads the scales, and how much the scales are pushing up on him will be r. So when you stand on the scales, you don't measure your weight, you measure the reaction between the ground and you. That's all you measure is r, not your weight. So you need to be able to draw free body diagrams to show these things. Now he's in a lift which is not moving. There will be a reaction upwards, and there'll be a weight downwards. They will be equal. So his reaction that he reads on the tops and on the scales will be equal to his weight. Here, however, it's just starting to accelerate upwards. It's accelerating upwards. His weight, as he reads it, or in other words, his reaction, is actually going to be larger than his weight. So we can draw it here. The reaction is greater than the weight. So r minus mg will give the acceleration. This gives the size of the acceleration. On the other hand, if he's at the top of the lift and he starts to accelerate downwards, then he's going to have a lower reaction. His weight is still the same. He is still going to have the same mass. He will still have the same weight at the same point in the gravitational field. But it looks to him that his weight is smaller. His weight is not smaller. His reaction is less. So the reaction is smaller than his weight, which is mg. So the reaction is smaller than mg. And the difference will give you the unbalanced force, the acceleration, mass times acceleration. So mg minus r is equal to ma. Now, if he were to drop completely, if the cable snapped and he accelerated downwards at free fall, his weight would apparently be 0. His weight is not 0. His weight is mg. He still has the same weight. The reaction is now 0 because the top balance, or the scales, are accelerating at the same rate that he does. We say here the reaction is 0. So mg minus r is equal to this unbalanced acceleration, which will be the acceleration due to free fall.